let's talk about vector valued functions. Now this is going to look very familiar. That's why I said that right there. And a vector shows both direction and magnitude. And I want to give you just a brief example of it. First of all, we write it with the brackets, or we could put xi plus yj. And not going to use that as much because this use of the I mixed with the imaginary number I. Anyway, super confusing. You may see it like this in some contexts. Generally in calculus, we will use this. So just very briefly, and not this, just quick. Taught this in other classes, and I would give them some vector like this, -2, 5. And I would say you're sailing a sailboat, and it travels with the vector of -2, 5. So 1, 2, 3, 4, 5. And you put a dot at -2, 5. So you might say, oh, that's just your coordinate. And I mean, I hear you. It's a coordinate. But if you connect it to where you started, which we will let be the origin in this context, put a little arrow there. That really means I'm traveling this direction and at that magnitude. So I have one sailboat that's going this direction. Okay, let's change it. It's not a sailboat. This is my canoe, and I am rowing in this direction with this magnitude. So it shows me the direction, it shows me the magnitude, but no matter how hard I row, here are the waves, here's the current. The current is flowing at, let's just call it 1, that's not a 1. Make it negative for some reason. 1, comma, 2, we'll do that. So what that really means is, even though I am rowing my canoe in this direction, the current is flowing in a direction of 1, 2. So I would move to the right 1 and up 2 more. And so I would connect the tail of this, well, the head of this one to the tail of the other one. So over 1, up 2, there we go. And that is the true direction of my canoe. So I'm rowing this way, but the current's carrying me this way. And so after, I guess, an hour, we'll just say that this has a unit of time of an hour. After 1 hour of rowing, I'm actually here. And I've traveled in this direction, even though I rowed this way and the current went this way. That's what vectors are used for. Okay, that was a quick lesson within a lesson, and let's just move on. The position, excuse me, is going to be x of t, y of t. That's parametric, right? So like this is going to look familiar because this is parametric, and it's also a mixture of derivatives and integrals, stuff you've seen before. So position, x of t, y of t. Velocity is, well, the derivative of position. The acceleration is the derivative of velocity. There's a lot of stuff happening here, but basically if my position is r, then my velocity would be r prime, which would be the velocity, v. And then the acceleration would be r double prime, which is v prime, which is a of t, and there it is. Okay, the displacement is how far I traveled on some time interval. And we've seen this before, but now we just have to do it twice, once for the x and once for the y. So the displacement vector, well, how far did I travel? Then, well, not how far did I travel? That would be total distance. That's a different issue altogether. But where am I in relation to where I began? What's my displacement? My x displacement is this. My y displacement is that. This does look familiar, again, because if I integrate a derivative, I get what I had to start with. So it would just tell me my x distance that I traveled, and my y distance. All right, the speed, also known as the absolute value of velocity. If I did that, I would end up with this. This looks a lot like the distance formula, or the Pythagorean theorem in a sense. So I would take the square root of the derivative of x squared, and then the square root of, hold on, let me get my words. Words are fun. I'm having a hard time with them though. X derivative squared plus y derivative squared, square root all that. It's the Pythagorean theorem, essentially. That's what it is. So a squared plus b squared equals c squared, but to solve it, I square rooted. Then the total distance traveled would be the integral of that you just saw. And then the average speed. This goes back to the average value of a function, and it's 1 over b minus a. It's basically like dividing by the length of time, or in some contexts, it doesn't have to be time, but basically divide by the width of the interval. And then this, of course, is speed again. So let's move on. Let's do that. A toy car travels along a path given by this vector for that time where distance is measured in meters and t is measured in seconds. Let's actually not even do the problems yet. Let's just grab a calculator and jump in. And I'm going to jump in with pressing mode and going to parametric. Even though it is vectors, it is totally parametric. So we're going to do it that way. All right, here goes. Y equals, and I'm going to type the stuff in. Sine of t, I am in radians, good to know. And then cosine of 3t. And this is for t greater than or equal to 0, so I'm going to press window, and I have mine starting at negative 2 pi, so I'll start at 0 and go to 2 pi. Good place to end this thing. So graph it, and my window is off. No, what am I going to do? Well, I'll fix it. Here we go. Zoom, standard, which actually does start a t value there. Oh my goodness, look at that. Isn't that neat? If you don't see it when it graphs, you miss it. So what I'm going to do is zoom in. And when I press enter at the origin, it's going to zoom in, and you can watch it graph. And this is basically the path that a toy car travels. There's a racetrack that looks like that. That's it right there. Okay, now we're going to find all kinds of different vectors and fun stuff. So let's get started. Find the velocity vector. The velocity is the derivative of the position. This is its path. This is its position. So there we go, bracket. Derivative of sine would be cosine. Derivative of cosine would be negative sine 3t. That's a chain rule, so times 3. There we go. That's the answer to the first one. Don't make it harder than it is. Find the tangent vector. Whoa, tangent vector. Okay, if I was going to have a line that was tangent to this curve at t equals pi over 2, then I would need the slope. So tangent, same thing, I've seen it before. Tangent is slope. So we're just going to figure out what happens if I plug in pi over 2. So the cosine of pi over 2, comma, negative 3 sine of 3 times pi over 2, so 3 pi over 2. And that is equal to, let's see, cosine pi over 2 would be 0. And negative 3 sine, 3 pi over 2 would be negative 1. So negative 3 times negative 1 would be positive 3. That's it. That is my tangent vector at pi over 2. Really quickly, I want to show you what that kind of looks like. All right, so window. I'm going to stop this thing at pi over 2, and then I'm going to graph it. And it's that right there. Okay, so what this means is I go, and my tangent vector would be 0, 3, and it's going to be going. That's it, time's up. Time's up, you don't get any more. It's going to be starting from here and just going up 3. Now, is it really going to go up 3? No, it's not going to go up 3, but that does represent its force magnitude. You can think of velocity, technically. That's its velocity at that moment. So as you saw this graph and it went whoop, then from here, starting like right here, it doesn't shift left or right. The vector is going to go straight up 3. Okay, let's move on. Total distance traveled by the car on the interval from 0 to 2 pi. And we are going to use, well, total distance traveled. It's that guy right there. So it would benefit us to have the derivatives stored in our calculator. So let's do that. And I'm going to do that like this. So we're going to let the derivative of the x1, y1 be x2, y2. So cosine of t. And negative 3 sine of 3t. And I'm going to do something different when we get to acceleration, just saying. So keeping in mind that the original function, original parametric equations are displacement, and then the derivatives are x2, then we will find the total distance traveled by plugging that in right there. I'm going to write it, but then I'm also going to type it in my computer. Calculator, abacus, slide ruler, whatever it is.
Would Jeremiah Standback please come to the main office? Jeremiah Standback, would you report to the main office? Jeremiah Standback.
We'll see if he goes. All right, cosine of t squared plus negative 3 sine of 3t squared dt. All right, I'm just using this formula for this question. That's it. So from 0 to 2 pi, and then I plug in the derivative of the x function, and the derivative of the y function, which I just did. So here we go. All right, math 9, 0 to 2 pi, square root of. Okay, love to type all that, not going to. Alpha trace, it was x2 squared, that's the derivative, plus y2 squared, and then dt. All right, here we go. What do we get? What do we get? I predict 13.065. That's my guess. Tried to do it in my head just then. Man, calculator must be slow, or the computer, or the abacus, or whatever it is. All right, this one takes a minute. So while it's doing that, what we're going to do is go ahead and deal with number 4, which is, okay, 13.065. That's good. That's good. It works. 13.065. All right. One day I'll teach you how to do that in your head. Or you could just, anyway, find that, why did I show you my secrets? All right, find the speed of the car at t equals pi over 2 seconds. So speed, okay, not integral, just plug it in, right? So square root of, and then x prime, so cosine of pi over 2, and then we're going to square all that, plus negative 3 sine of 3 pi over 2. We're going to square all that, and then square root this thing. And actually, we can do this one in our heads, and we're going to, so don't panic. You got this. Cosine of pi over 2, you actually just found this. Cosine of pi over 2 was 0, so we have the square root of 0 squared, which is totally pointless, but we'll write it anyway. And then this is sine of 3 pi over 2, which is negative 1, negative 3 times negative 1 is positive 3. 3 squared is 9, so 3. Okay? I want to put units on this one because I really want to make sure that I understand the context of this. This is the speed of a car, and we are measuring time in seconds, distance in meters, so this is meters per second. And so if you want to, you could say that this is going to be meters. It's the total distance traveled by the car. Acceleration vector, okay? Well, let's figure that one out as well. I want to find the derivative of the derivative, and so we will do that, but I'm going to shift gears a little bit on the calculator when I do this one. I just think it's going to be fun and a good solid example of how to use the calculator in these contexts. In the meantime, acceleration vector for the car. Notice that they told you what t-value to plug in. So first I need to find the acceleration vector, which will be the derivative of that, which will be negative sine t, comma. And then the derivative of this, which would be negative cosine of 3t, and then times the 3, so 9. So negative 9 cosine of 3t. Okay, that is the acceleration vector, but I want the acceleration vector for the car at a certain t value. So I'm going to plug in pi over 2. Now, here goes. Y equals. We have the original set of parametric equations that show the displacement. We have x2, which is the derivative, and now we're going to get the third one, which is the derivative of the derivative. And at this point, things seem to get a little bit out of hand because you're taking the derivative of the derivative, but you've dealt with it before. So you could type negative sine t. Totally cool. Could do it. Great. I don't know why it's not highlighted there. Oh, because that one's not typed in yet either. Or you could, and I love this, and you've seen it a million times, math 8. Okay? We are going to take the derivative of what we already have. We could have done this for the first derivative and then just kind of nest them. So do this for the first derivative and then do the second derivative that same way. You can only do that about 3 or 4 times before the calculator's like, can't compute that. But anyway, the derivative with respect to time of the x2 function at any given t value, and then math 8. All right, notice they're both highlighted now because there's typing in them. ddt of y2 at any given t value. So whether I find it this way or whether I have it this way, I'm going to get the same thing. So what I want to do is evaluate, let's quit, second quit. I want to evaluate this at pi over 2 and this at pi over 2. Totally could do this by hand, like totally could, but I'm just using this as an opportunity to show you some calculator tricks. So alpha trace, there's that at pi over 2, and there we go. That's negative 1. Let's be real honest. The calculator can only figure it out so well. And then we'll do the same thing. pi over 2, and that is 0, and it truly is 0. So the acceleration vector for the car at this specific time is going to be, here we go, I'm going to put a little bar here where I say t equals pi over 2, which means I plug a pi over 2 into both of those, and I get -1, 0. Totally could have done that by hand. And then, last one, displacement vector for the car on the interval from 0 to pi over 4. Displacement vector. Oh, there we go. So I need to use the derivative on an interval to figure out how far I traveled. Makes sense. So let's do it. From 0 to pi over 4 of the velocity, which we found to be cosine of t, so cosine of t dt, comma, same thing, 0, pi over 4, and then -3 sine of 3t dt. And this is equal to something. We'll type it in the calculator very quickly and figure it out. Here we go. So math 9 and 0 to pi over 4. And let's figure this out. Second in calc, and we're dealing with the derivative, so y2. And this is going to be 0.707. Yeah, 0.707. And then the other one, second enter, by the way, pulls up the last thing you typed. You can go back and edit it. Let's do that. Alpha trace, y2. There it is, -1.707, and we now have the displacement vector for the car on that interval, which really tells me, well, I traveled from 0 to pi over 4 a sum quantity, SUM quantity, of this far to the right and -1.707, so 1.707 down. All right, so 0.707, comma, -1.707, and that is it.